This is what we did last time. Wonder if anybody has any questions about this stuff. Right. So just to go through it really quickly. Okay. Bitwise operators, right, and or not XOR and XNOR. We don't have XNOR here, but and then there's a shift and circular shift, right? And then we did we talked about this. Like Python is different in the way that it handles integers. Okay, Python can handle big integers. Right, like in C or Java, and these have fixed size integers. So when you shift, usually you have a 32 or 64-bit integer, and if you shift more than that, you'll just remove all the bits that you have, right? And like here in Python, if you shift right, the left side gets zero filled, right? Filled with 0 bits. And so this has 1, 2, 3, 4, 8 bits, right, in here, this binary integer. And if you shift bits, shift 8 bits to the right, and then you get a 0, right? And if you, like, in Python, if you shift left, right, if you shift that way, you'll never get a 0. I don't know, maybe you will if you shift like 3,000 bits or something. I don't know what happens then. We can try it. But if you like shift anything like how many 32 bits or 64 bits, you still get an integer. So Python is different in a way that it handles huge integers. So it always gets I mean, shift always works. Order of precedence, like you have in regular algebra, right? So OR, think about OR is kind of like addition, right? And AND is sort of like multiplication. And NOT and those kind of unary operators. You guys playing game or something in that? Then we talked about Boolean algebra, right, last time. And so Boolean algebra, we have these basic operators, not and or. Actually, XOR and XNOR can be described or can be expressed using these three, right? So these three already is a complete set of Boolean operators, right? Like XOR could be expressed this way. It would XOR Y, right? Exclusive or Y would be equal to X or Y and not X and Y. Right? These two are equivalent, and XNOR is the same way, right? You can, so that's what we did last time, and all these laws, okay, all these laws, you do need to remember them. If you do remember the laws of basic arithmetic, right, that you learn in school on the regular math, these things would probably look quite similar to you, right? Commutative laws basically means that you can, switch things around. So it's like X times Y equals Y times X, right? It means the same thing. This here means X and Y. equals to y and x. And so these laws you have to remember. Okay. So we talked through a few of those problems, right, from the contest and from the wiki. That's what we did last time. And so that's it. What we want to do a little bit today is this. We did say something about last time that in bit operations, right? In bit operations, you have a difference of signed integer and unsigned integers. All right, we talked about a lot of times you see the most significant bit in an integer as is used. It's a common practice in machine language programming, and use that as a sign of the integer. And consequently, the same is true for languages like C, C++. These are C, C++ is actually the closest to machine language. Right? You can actually write assembly computer instructions basically inside a C program, and C compilers are able to handle that. So in this case, in these languages, these fixed size integers are called primitives. Okay, primitives meaning that it's like an atom, right? An atom, if you break it apart, it no longer has the characteristics or it's not the matter that it makes up anymore, right? Because atoms, if you have a bunch of atoms like carbon, right? A bunch of carbon, you can have pure carbon, right? That makes up a chunk of some matter, some material, like diamond, right? It's basically a chunk of carbon. And at the atom level, it's still a carbon atom, right? If you break apart the carbon atom, it's no longer a carbon atom anymore. It's still some particles, right? It's still material, but it's no longer. So atom is like the least, the smallest thing that you can that you're not able to break. If you break that, it's no longer an atom. It's some other little particles. In these languages, right? Primitive, meaning that these integers you cannot break them. They don't have components, right? If you break up an integer, it can still, like, an integer still have bits in the right, binary. So that's what it's called. The reason why is that this actually makes mathematical operations like negate, meaning like one turn into -1 or 10 into -10, addition, subtraction, and all these easy to implement at the machine level, okay, with in digital circuits. That's basically the reason. I want to give a few examples, like with an 8-bit integer, right? This is basically what Intel had when they created the I forgot what they call it, 8008. That was their 8-bit CPU, right? Back then, this is the the largest integer the CPU can handle natively, right? If you want to handle any so for an 8-bit integer, if it's not signed, if it's unsigned, right? The value range is 0 to 255. Right? That's 8 bits of 0, and that's 8 bits of 1, right? From 0 to 255. And if you make it into a signed integer, then the range would be from minus 128 to 127.
So why is it not 128?
Huh?
Never mind.
Well, actually, that is 128, right? Minus 128, I'm sorry. Right? That is 1. The highest bit is 1 and all zeros. Right? That's minus 128. And this is minus 1. Right? Using the highest bit as the sign of this integer. Okay, and positive numbers would be from 0. Well, 0 is not positive, but you understand what I'm saying. From 0 to 127. Yeah.
Why is the odd one negative 1? But all one in the negative is fine. Negative 1 is not.
I think what he means is why is the positive number like the and it turns into like a negative for
I mean, the why, I'm wondering why like a negative sign integer with always 1, negative 1, and not negative 130.
Yeah, actually, that's a good question. Here, if you look at the explanation here, you can see in decimal you have this equation, right? Minus 1 plus 1 is 0, right? And so if you look at this number, and if you add 1 to it, what happens? It's 0, right? Because if you add a 0 here, it creates a carryover, and then it carries over all the way over here. That creates an overflow, right? That bits go away because we only have 8 bits here, right? See, this is how that makes this type of basic algorithms easy to implement in computer circuits, right? Because in circuitry, if you want to, let's say, if you want, because this is the somebody knocking the door. Oh, sorry. Okay. All right. So in decimal, you have n equals minus. Well, if you double negate a number, you get the number itself, right? But in this kind of limited binary format, this is how you do negation. This is minus n, right? And we actually, so minus 1 if n is minus 1, right? So minus n is 1, right? And if you do a negation, which meaning basically turn on, flip all the bits, right? So it's 0, 0, 0, 0, 1. You flip all the bits and then you add 1 to it. That's how you do this negation in digital circuitry, right? The way that this looks complicated to us, right? But the reason that it is easy to implement in computer circuit, for example, the reason is that whatever number you have here, right? If you have 1, right? If you want to get negative 1, you just need to flip all the bits of 1 and then add 1 to it. Right? That's easy to do in circuits. Right? It's harder for us to wrap. Maybe, I don't know, maybe it's easy for some to understand, but if you have any, you know, it is one way that, you know, that we have to think about, right? To do that. But this is an easy way to get a negative number out of a negative integer out of an integer, right? In computer circuitry. Right, so let's say this is 2, right? And this is 2. And negative 2 would be this. And if you plus 1, right, add 1 to it, you get 1. Oh, sorry, you get minus 1. So negative 2. This is, let's hold on, I got it wrong actually. This is actually sorry, this is minus 2, right? What I'm trying to do is make this is this minus 2. So so what I'm trying to do here is this is 2, and if we turn it into minus 2, it would be that, right? And actually that would be minus 2 add 1, you will get oh, what I'm trying to do here. This is so that is oh, let me see. Yeah, this is right. Sorry. I was trying to say is we want to do let me see. Oh, what I was trying to do is to illustrate this, right? This is 2, right? This is 2, and we want to do a we want to you know, prove that this actually gets you this 2, right? So that number would be minus 2 in here, right? Negative 2. This is negative 2. If we want to do and then do a negation, right, or not, flip all the bits and then plus 1. This would be 1 plus 1. You'll get 2. I'm trying to demonstrate that this is the conversion there, the formula for conversion there. And so you can see that this allows you know integer negative integer, you know, and then integer addition, integer subtraction, easy to implement with digital circuits, right? Because you can basically use those 3 operators, right? Negate, and OR. Right? With those simple circuits, you can implement addition of binary integers, right? And then actually in the initial, you know, days of micro CPUs, all the rest, like if you need to deal with any bigger integer than these, right? Then you have to write a library, you know, to do that, basically to handle, you know, longer integers. So that's all that you know, bit bit operator stuff. So after that, we were supposed to do digital electronics. Okay, this is one type of problem in ACSL contests, right? And if you look at the digital circuit stuff, they're actually the same things we have talked about, right? So you have, this is what they call, ACSL calls it a buffer. I call it a no-op, right?
No,
Yeah, so there's no operation. It's whatever in, whatever comes out. So this is actually, it's just, I guess, for completion of this whole thing, but, and then this is not, right? This is a symbol for a not gate. Okay. And then this is N. This is a symbol for N. And this is the symbol for OR. And this is the symbol for NAND. NAND meaning you do AND, you do A, N, B, and then negate. Right? This is the same thing as similar to that, but you do A or B and then not negate, right? And here is exclusive or A or B. And then this is exclusive or and then negate, right? So these are the basic symbols for digital circuitry. This is what all the computer stuff are made of. And if you guys, I guess, ever get into large scale, integrated circuit design in the future, when you go into EE, right? Electrical engineering. And the circuit design is basically everything. You don't do it at this level anymore, right? Because nowadays the circuits are designed with huge software that has all these logic that's buried underneath a lot of components that you can already use, right? It's basically like you write software today, these days. You don't need to worry about, for example, in Python, if you want to do number crunching, right? If you're doing statistics, like basically all the data science these days, right? You use languages like Python or R. So you don't really need to worry about like 1 + 1 = 2 type level of mathematics, right? You don't do that anymore. So you just take a huge array, for example. You can do an array times an array, or an array plus an array. You do math at that kind of level. And that allows you to do stuff like all the graphics, the GPU, right? All those kind of things, or all those kind of logic are already built into the circuitry, right? So today, the computer engineering and computer science have, evolved, right, over the last, say 60 years, 70 years, 60 years. Yeah, 60 some years. So you don't need to worry about this level of logic anymore, right? But this is the basics, right? All those libraries and all those in EE, when you design large scale, integrated circuits, like if you design a new CPU, right? You have all these logic that's already built into a block of circuits for you, right? You need to put them together, link them together, and the software would do, the interconnection and optimization and all that for you. Because people build these logic, right? But at the very basic level, these are still the particles, right? Like if we're dealing with physics, right? The physicists, when they break up an atom, you get electron and proton and all those things, right? This is what you're looking at. And if you break up a CPU, a modern CPU, right, they'll probably have millions and millions of these things in them, right? Or even billions, I don't know. Right. So this is basically what makes up your computer, your phones and my laptop, all these kind of stuff, right? And so this is a problem that ACSL contest would show you, right? Would ask you to solve, like this one, right? So if you look at this, what they ask is usually you have in here you have 4 inputs, right? So what do you get out of here? This is the output side, right? So you have 2 ways to deal with these type of things, right? One, the truth table we talked about last time, right? And the other is Boolean expression and simplification, right? For example, this one. Right, so if we are dealing with this, we can see that we have these gates, right? And these are just a knot. That's easy. We'll just handle it here, right? At that point. So we have like 1, 2, 3, 4, 5 things here to worry about, right? And so what is 1? This is a AND gate, right? This means the output here is this and this, right? What is this? This is not A, right? We have this not gate here, right? So this is a negation. So this is not A and B that would come out here, right? So that's what I mean here. 1, the output 1 here is not A and B, right? And now let's talk about 3 first. 3 is C, D. This is OR, right? And then negate. So it's C or D and then negate, right? That's 3 here. And 2 is, this is the same thing as this, right? So this is basically a branch of that. So this is the output. The input here is the output from here. And the input on this one is not B, right? So B and then negate. So it's not B or 3, right? Or this thing from here. And so 4 is a exclusive OR, right? Exclusive OR, and then the result from here and here. So it's 1 and exclusive OR 2, right? And here 5 is the, that where we get the end result, right? It would be the result of 4 and exclusive OR result from 3, right? So it's 4 XOR 3, right? So we list all that here. Yeah, we list all that here. And then in the end, 5 equals to 1 exclusive or 2 or exclusive or 3. Right. So it would be right. And then in the end, that's the Boolean expression of this circuit. right? So basically that is one way to get the result. And of course, sometimes they would ask you to simplify that, that we talked about last time, right? And okay, all right, that's what all those mean there. And so with truth table, so we got this expression out of that circuit, right, from here, right? So that's what I copied over here. And so with truth table, that's what we list here, A, B, C, D as inputs, right? And then we basically iterate all the possibilities for A, B, and C, and D, right? So it starts from all 4 zeros and what you get. So not A and B, that would make all these zeros because B is 0, right? B is all 0 here. So that's all 0. And C or D would be C or D and then not, right? Would be this is false, and then come over here becomes true because you have this negation here. And then all these 3 creates true, right? It negates, becomes false. So that's how you generate the result eventually, right? So you get the intermediate results, and then you get the second level intermediate results, and then you get the final result in this column, right? And so we have to iterate all the combinations of A, B, C, and D, right? So now these are 1. Again, we iterate different values for C and D, and then A becomes 1, B is 0, right? And we iterate C and D combinations again, and eventually A and B both are 1s, and we iterate all those. So there, with basically 4 inputs, you have 4 of these, right? So you have 16 possible combinations for the inputs, right? You got A, B, C, D, and which is 4. So if you have 2 inputs, A, B, or let's say if you just have C, D, right? You got 4 different combinations. And if you have 3 inputs, you got 8 different combinations, right? You got 4 bits, right? 4 different inputs, then you have 16. And if you got 5, then it doubles again, right? 32. And if you got 6, it would be 64, right? So, so you can see that, I mean, if you're using the truth table, you can do this, but it would really be beneficial to use a software to do it, right? Rather than doing this whole thing manually. But, this is one way of, resolving these Boolean operations, right? And basically Boolean operations give you a mapping between the circuitry to Boolean expression, right? And so the next problem is quite similar, but this is asking us to do simplification, right? So we have this circuit here. This is a problem that you will get, right? So this is a circuit. As we can see, one is basically A and B, right? This is N. Is that N? It is N. No, this is, wait a minute. Oh, it looks like OR to me. I don't know. It is an OR. Well, if it is an OR, then I got this wrong, right? So if it is an OR, oh, come on. If it is an OR, let's do that. If it is an OR, then one is A or B, right? And two is B or C and then negate, right? And three is not A and this, right? From this output from one. So and four is again N, right? It's 3 and 2, right? Those are correct. And so it would be this, right? Not A and A or B, right? So what can we do there with this? Where do we? Okay, the loss. Right. So the loss there. Oh, we don't have one, I guess, for that. So this would be actually
It will be A and B.
copy this over. Right. Right. And then that part is 0, right? 0 or right. So this is actually just equals right. So the result would be this is 3. So this would be this, right? And this would be actually so we still get 0, right? Because you got You got B and not B in this expression, right? So the end result is still 0. So that's, again, this is a second type of problem that you can encounter in the ACSL context. Right? Does this make sense? These are basically the laws that we talked about last time here, right? That is this De Morgan's law, right? De Morgan's law says not A or B equals not A and not B, right? So that gives us this, make this into not B and not C, right? And now we can just take the parentheses out of this expression because we got and they're all and operators, right? So that's the associative law, right? So now if whatever the parenthesis basically doesn't matter anymore, right? In this expression. So we take the parentheses away, then we got B and not B in the expression. That makes it 0. And if you have end, I mean a 0 in an end operation, right? It becomes 0, always 0. So that's it. These are the types of problems we will have in circuitry. Now let's take a break of 5.
Bill was unaware. No, okay, I can't tell you what that time. Just if your arms look at slip over. I can't tell you. These questions are easy. I just spent my past time trying to fit these with this answer. It's a first. I looked out what the examples. The first thing is always the Morgan's law. Like, look at the Morgan's law. I don't know. You always use the Morgan case. I don't know why. So what the Morgan, you know what those? And you should do that. Solve this, the question right in front of you, so it's there's also a second version which looks like this.
No, I don't think so.
So it changes to not over multiply equals plus. And not over plus.
Hey guys, don't break anything. I'm gonna just, yeah, 4, 5. Okay, let me try to do this. Okay, here. So here is not a, this is an end, right? So not A and B, which was not A and B. And then come here would be not A and B. That's the input here, right? And then this is just B. Right? That would be or B. And then not, right? Right, that's the end result. And so if we do truth table would be A, B, right? And here would be not A and B. Right, here would be the end result. Right, so 0, 0, 0, 1, 1, 0, 1, 1. That's the 4 possibilities, right, for 2 inputs. And so not A and B. So because and B, if B is 0, it would be 0, right? So these two are 0. Right? And not A and B, this would be 1, right? Not A would be 1 in that case, right? And not A and B in this case would be 0. Right? Right? And then the end result is this or B, right? So this or B would be 0, 1, 0, 1. Right? So we got 2 pairs, and the 2 pairs are 0, 1 and 1, 1. Right? So the 2 pairs are, it's basically A, B, right? Equals 0, 1, or 1, 1. Right? These are the 2 pairs. Anybody has different results? Because this should be easy, really. Right? And then the second problem, right? So we have A or B here, right? This is an or. This is an and, and this is an and, then not. So for that, we have A or B, right? That's 1. That's here. And then here is B or not C, right? This is not C. That's N, not C. That is B and not C, right? And then this is an end. So we got end and then not. Right? So that's the expression for the second circuit. Right. So now it's asking us for all the triples. So we got A, B, C as inputs, right? So with this, you got 0, 0, 0, 0, 0, 1. So we got 8 combinations, right? 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Right. So these are the 8 different combinations, right? And so we got A or B, and B and not C, right? And then the, well, do we need well, let's just do the result here, right? So A or B would be, let's just do that, right? 0, 0, 1, 1, 1, 1, 1, 1, right? Right, that's A or B in here. And then B and not C. B and not C, because there's B there, right? So if B is 0, we got 0, right? 0, 0, and then not C meaning that if C is 1, we also got 0, right? And then this is 0. So B and not C, this is 1. B and not C, and this is 1, right? So we got 2. Right? B and not C, right? So if anywhere B is 0, we got 0, right? 0, 0. I mean 0, 0, 0, 0. And then anywhere C is 1, we also got 0, right? So C is 1 here, we got 0. And C is 1 here, we got 0. And the rest are 1s. Yep.
You forget this like scripture on the first question because there's a line.
Yours different. Did I forget something? Question 1 is that so not A and B, right? Not A and B. This is not A and B, the result here. Not A and B. So anywhere B is 0, we got 0. Yep. Oh, well, no. So we got 0 here and here. Right, and then not A. So if we have A is 1, then we also got 0.
So like the line at the very top, like with the answer
Oh,
between all the zeros between 1 and all the 1 becomes 0.
oh yeah, you're right. Yep, you're right. So actually, it's actually the other way around, right? So it's 0, 0, and wait, 0, 0, 1, 0. These two pairs. All right. Thank you. So let's continue on. Second one. Thanks for that. So we got A or B, right? A or B so far. We're correct, right? A or B. Yeah. Okay. And so B and not C. B and not C. So anywhere B is 0, we got 0. And so not C. Only when there's 0, right? B is 1, C is 0, B is 1, C is 0, we got 1s. Okay, so now we do the end of these two, right? And then again, there's a flip, there's a negate at the end. So that becomes 0, 0, we got 0, and so this becomes 1. This becomes 1. This becomes 0. And this is 0 becomes 1, 0 becomes 1, 0 becomes 1. This 1 becomes 0 and 0 becomes 1. So now all the pairs that makes, all the triples that makes the end result false. Right? So we got those two, right? Those two rows. So it's 0, 1, 0 and 1, 1, 0. Right? So those two triples are what this problem is looking for. Okay.
I first I did this by simplifying it, and then I got not 1 and not 2.
That's a good way to do it, actually, right?
But then the answer is actually 4. It's not 2. It's not 3, right?
Okay, let's try that. So if you simplified this, this is the initial equation, expression, right? Do you have the same? It's the same starting point. So that would become not A or B, or not B and not C, right? Right? That's one of the De Morgan's law, right? And now this becomes let's see. Can we really simplify it? Or this would be A or B, not, or not B, or C, not, right? So it would become A or B, not, or B, not, or C. That's
And you get rid of the and the overarching not.
right. When you get rid of the overarching not, then this end becomes or. Right. This becomes this part not, or the later part not. If you look at the De Morgan's law, that's how it is, right? The De Morgan's law would be this, right? X and Y equals, or it's X or Y equals. That's the two laws in that set, right? Yeah, this still simplifies a little bit, right? I suspect that the result would probably be the same, because we got two ors here, so it's going to be a lot of there's going to be more true sets, more true result than false. And so I suspect that you will get the same thing here. That's a good one. Yeah. Sometimes you can maybe you can't really simplify it to the bones, right? But you can still do a lot of it can still help a lot when you're pressed for time when you're doing the stuff at contest. Okay, that's the digital circuit type of problem. Now let's share the screen again. Okay, the next thing we're going to cover are this thing called data structures. ACSL actually doesn't really have a whole lot of requirement or a whole lot of data structure emphasis. In reality, I mean, when you're a software engineer, you're dealing with a lot more in terms of data structures, right? Especially when you go to I guess any modern language today can deal with objects, right? So you have you have that always. But in here, there's a set of basic data structure things that that we want to talk about here. The simplest thing is probably list, right? List meaning that you can have a list of things, right? That's basically, and what you can have out of the list is, you know, how long the list is. And then you can add, remove from add into the list or remove from the list, and access members in the list, right? And then you can do search and sort. These are the type of operations that you can do on list. All right, the next thing is stack. All right, a stack is, I mean, just by the definition of the word, a stack meaning that you can stack a bunch of things, right? When you stack a bunch of things, like if you look at this, you have a stack of boxes, right? So basically the stack means that it's going to be really hard to get things out of the box. So basically in software and programming, stack also means, you know, you have the concept of bottom and top, right? And then the characteristic of the stack is first in, last out. Where did I copy that? Or I just first in, last out, right? This is first in, last out. And actually, yeah, I basically got somehow. So basically that's the characteristic of stacks, right? So you can push things into the stack, and really that's how, you know, most of implementations of stacks give you, right? There's a push operation, and then there's a pop operation. So you can push things into the stack and then pop things out of the stack. And usually the like if you want to implement something in an object-oriented language, it's usually stack, right? It's usually something like this. It would be stack, right? Push item. Right, that would be an example of how a stack works. And And then when you pop something out of there, it would be something like a variable x equals, right, stack pop. Right. These are sort of examples of how you would use a stack in programming. And in the ACSL, in the ACSL stuff, they also use this type of syntax, right? So you can push something into a stack and then pop something out of it. Oh. Actually, you gotta pop something out of something, right? The stack is usually also a variable, so that's why it's usually in real programming, it would be really something like that, right? And optionally, some implementation allow you to peek, right? Take a look at what is on top, right? Or if there is anything on top, because the stack could be empty and things like that, right? So that's stack. And the next thing is queue.
Yeah, I got a question. So for the peak, is it stack dot peak? There's the,
Yeah, it's basically like pop, but you don't pop, right?
yeah.
You just peek, take a look.
We can do peak item.
Nope. You can only peek on the stack, right? You can only peek that stack and you see what's here, right? If there's anything there, right? But really, you're peeking at the stack, not the result. I mean, the peek function usually will give you the item back, but the item is still on the stack. That's what it means, right? And so the next thing is queue. Queue is basically like humans, like we queue, right? We queue for, different things. And that's basically, you have the concept, the characteristic of front and back, right? And then this would be first in, first out, meaning that the first one gets into the queue is in front of the queue, right? And so if you are going into the, the Department of Transportation and getting some license or something, you get into a queue and the first person in the queue is the first person gets served, right? Get the service. And so the operation here would be, in queue and DQ, right? And then there's also the concept of priority queues. Well, we'll talk about that in a little bit. And the next thing is trees. Right? Trees, as we understand it, right? But trees in computer setting, trees, I mean, the natural trees, the root is down there, right? And leaves are up there. But in computer trees, the root is up here, right? This is the root. And these are branches, and down there at the lowest level, these we call leaves.
Works are two, like only root and another level.
Nope, you cannot have that. Then that would become multiple trees, right? That's not one tree anymore. So tree operations, let's say it does allow you to like delete nodes, right? So if you take these nodes out, then you have to regroup this tree. Right? Basically, you have to, link them somehow and make it a tree again. And so you have the concept of root, branches, and leaves, right? So this is the root in this tree. And for these are branches, right? And then at the bottom level, these are leaves. Leaves are basically the ones that don't have any children, right? So in here, this at each level, right? This is a parent node, and then it has two children. This one also, this one is a parent has with two children, and so there's the concept of binary tree. Binary tree basically is a type of tree that every node has two or less children, right? It can only have two or one or zero, right? This one has two, this one has two, and this one has one. And then, I mean, this one has one and these ones have zero.
How the children relate to their parents?
It's basically when you implement a tree, you basically have a node, right? A node, you have a storage unit to contain the whatever is the tree contains, right? This one, say each node has one character. You have a storage for this, and then you have two links to your children, right? So these are that would be a binary tree.
What the children feel differently from their parents? Are they just other containers that store anything?
No, because for this one, if it does not have children, then those two links would be null, right? Would have nothing. But this node would still just contain its own character. But it does not need to have a, well, I shouldn't say absolutely, but some implementation do, have a storage unit here to have a link back to its parent. But usually that's not the case. Usually it's basically just parent have links to its children. Right? Because when you implement these operations like sort or search or traverse meaning basically walking all over this tree, right? Walking the whole tree. So when you do these operations, you actually, we have talked about recursive functions, right? Basically, you're dealing with recursive operations here, right? For example, if you want to traverse this tree, basically you're saying, I want to traverse this whole tree from the root node, right? So to do that, I'm going to go to this. I'm going to traverse this branch, this whole branch first, right? So you recursively do the traverse function, go down here, and then if this have any children, then you again traverse the children here first, right?
Wait, so traversing is just like looking.
Right, you're just walking through the whole tree, basically walking through every single node of the tree. That's called traverse. And when you do search, for example, you have to traverse the tree, right? And also
Wait, but search is like searching for specific.
specific character. For example, I'm trying to find the E in this tree. How do I do that? I'll have to basically walk the tree and until I find the node, right? Until I find the E, right? But you don't have to continue walking the tree if you only want to find just one E, right? But if you want to find all the E's in this tree, you might have to do a little more. But again, if this tree is sorted already, so in binary trees, we have, balanced binary trees. So that means it would be, we're almost done. So this is a tree structure. And then ACSL has this concept about using a binary tree to implement priority queues. But that only gives you, two kinds of, so basically it would be a tree with these different levels of priorities, right? So basically, if you have, if it is linked in that manner, and the least, the ones that have the smallest item would be on top, right? And on each branch, or for the whole tree, the root node would always be the smallest, right? And then because when you say want to dequeue something from this, based on its priority, you can say this one with the smallest goes out first, right? Is the front of the queue. And then you can just compare these two nodes. Which one is smaller? That one becomes the root, right? So basically you can have a way to implement priority using a binary tree. And I think that's it. All right, thank you guys.
Thank you. Wait, Thomas, your pencil.